Here's a question for pilots. Is your number one concern getting there, or is it safety? Of course, it's getting there safely. To take off effortlessly and land consistently with a stabilized approach, knowing your AOA is crucial for safe operation. To handle that issue, let me introduce Alpha Systems AOA. If you haven't heard, Alpha Systems AOA makes the revolutionary angle of attack indicator. With the Alpha Systems AOA indicator in your cockpit, you don't have to feel or guess how close to stall you are during the turn to final, because you've got an electronic indicator at eye level showing how much lift your wing is producing, and that's critical. Bottom line, Alpha Systems AOA saves lives. To find out more, visit alphasystemsaoa.com. alphasystemsaoa.com. FAA approved. Alpha is ready to upgrade your aircraft avionics package now. alphasystemsaoa.com. That's alphasystemsaoa.com.
This video is going to talk about an angle of attack system developed for the MU-2. Alpha Systems tailored their system specifically for the airplane. Test flying was accomplished on a Marquis and Solitaire airplane and was approved by the FAA in March 2016. We're going to talk about why angle of attack is important, how to use angle of attack, and the real safety benefit of an angle of attack system, how it will save you if the airplane gets near a loss of control situation. Why angle of attack? To increase safety. How? By providing the pilot a precise means of measuring margin from stall directly. No more adjustments for gross weight for flap position or other things. Takes the guesswork out of flying the airplane. So let's start with an engineering lesson, because that'll give you the background to understand why angle of attack is important. So let's get started. First, what is angle of attack? Let's go all the way back to your initial pilot training. You may remember the old FAA videos. Goes back a way, doesn't it? And now the engineering lesson. This video shows what is really going on with the airflow over a wing and how it affects the way the wing works. Notice that as the wing angle changes, the flow also starts to change, especially as we get to the higher angles. Eventually, the flow separates from the top of the wing. This is what happens when the wing stalls. Let's define a few terms. Angle of attack is defined as the angle between the chord line and the relative wind. The chord line is defined as from the leading edge of the wing to the trailing edge of the wing, we draw a straight line. The relative wind is exactly opposite to the flight path of the airplane. That's how the air is going over the wing. And the angle of attack is defined as the measurement of that angle between the chord line and the relative wind. Often, engineers, we give the term alpha to angle of attack, hence the name for Alpha Systems, where that comes from. So what did we learn from the video that showed the airflow around the wing? As angle of attack increases, airflow begins to detach from the top surface. This can happen even with a constant airspeed, such as in level turning flight when pulling Gs. At higher angles of attack, flow over the airfoil starts to separate at some angle. Usually this is around 15 degrees. The flow is almost completely detached from the top surface. At this point, the wing cannot generate enough lift to support level flight, and the airplane will start to descend. This is the critical angle of attack where the aerodynamic stall occurs. So let's look at that video again and pay attention to where the flow separated. You saw the flow separate? So let's just play that video again. See where the flow separated. That is the critical angle of attack where the wing stalls. The important takeaway here is that stall is a function of angle of attack. It's purely related to the airflow and the angle of the airflow with respect to the chord line of the wing. The wing will always stall at the same angle of attack. This is the key point in all this, so let me repeat. The wing will always stall at the same angle of attack. Airspeed is not a good way to measure stall. because the stall speed changes with weight, load factor, bank angle, flap position, engine power, etc. But these are the big ones. In fact, the airplane can fly at zero airspeed, and airplanes doing aerobatics make use of this to fly many of those maneuvers we are fond of seeing at air shows. Airspeeds typically memorized by pilots are for maximum weight and forward CG, and higher than actually needed for other weights. On the other hand, regardless of the weight, load factor, bank angle, etc., the wing will always stall at the same angle of attack. So how do you measure angle of attack? Angle of attack can be measured a number of ways, and the Alpha Systems system uses a probe mounted under the right-hand wing. The probe has two small holes on it, and as the airflow changes, the differential pressure between those two holes changes as well. The Alpha Systems measures the difference in pressure between those two ports. This system has been used for many years. Flight testing of airplanes has shown that this is a very accurate and reliable means of measuring the angle of attack on the wing of the airplane. The Space Shuttle uses the identical principle to measure its angle of attack during approach into the atmosphere. The ports, however, it doesn't have a probe, but the ports are drilled into small little holes on the nose cone of the Space Shuttle, and they measure the differential pressure between those two ports. Angle of attack is a fundamental principle used by aero engineers to quantify the aerodynamic forces acting on an airplane. Angle of attack affects them all: lift, drag, all of the aerodynamic forces acting on the airplane. The graphic shows how these are related. So let's try to visualize what happens as the airplane changes angle of attack and how this relates to the lift curve slope. So in this graphic, the flight path of the airplane is defined by the purple line. But what does the flight path really mean? The flight path is related to the direction of flight of the airplane. And the direction of flight of the airplane can be either climbing or it can be descending. And remember from our engineering discussion, we had the relative wind is exactly opposite to the direction of the flight path. So there's the relative wind, there's the flight path. So let's stay with the relative wind because that was the engineering definition. And the angle of attack of the airplane can change. Angle of attack can increase, angle of attack can decrease. And remember, the angle of attack is the measurement angle between the relative wind and the nose to tail line of the airplane. And the angle of attack now hasn't changed. The airplane's descending, the airplane's climbing. Angle of attack is identical. Doesn't matter. Angle of attack increases, airplane's descending, angle of attack can change again. So the angle of attack is always with respect to the relative wind, as you remember, is the opposite of the direction of flight of the airplane. So let's walk up the lift curve slope. Note the angle of attack indicator changes as the angle of attack changes. This is approximately at VREF plus 10 knots. When the blue begins to appear, the airplane is in the approach regime. Here the airplane is at VREF plus 5. Here the airplane is at VREF. For the MU-2 installation, this is corrected for flap settings and gross weight is automatically adjusted, as this device is truly measuring angle of attack. And from the previous engineering discussion, you should remember that angle of attack directly measures the lift capabilities of the wing. VREF is always defined as a percentage margin from stall. For the MU-2 system, this is 1.25 for flaps 0, 1.25 for flaps 5, 1.3 for flaps 20, and 1.5 for flaps 40. When the red alone appears, the airplane is in the danger or do something about its zone. Here the airplane is at VREF minus 10.
Too slow.
When both red chevrons appear, the system also presents the too slow voice alert into the pilot headsets. This is approximately 5 knots prior to shaker. If you continue increasing angle of attack, the next warning is the stick shaker.
Stall.
About 5 knots prior to aerodynamic stall. If you have the voice alert system installed, at shaker you also get the stall voice in the pilot headsets. And if you continue increasing angle of attack, the airplane will stall. Now let's look at a real-world straight and level stall. This shows what the angle of attack indications are relative to the airspeed and demonstrates the early too slow message and thus early stall warning provided by the angle of attack system. Pay attention to the angle of attack indicator and the airspeed. Here we're starting at a VREF of about 106. Next is the too slow voice alert. Airspeed is 92 knots, pitch attitude 5 degrees. This is about 5 knots prior to shaker. Then comes the shaker, and if you have this voice alert, the stall in your headset. Airspeed is 87 knots, pitch attitude 9 degrees. This is about 8 knots prior to aerodynamic stall. And finally, aerodynamic stall.
Stall.
Airspeed is 79 knots, pitch attitude 9 degrees. Note the vibration and buffeting. Lower the nose to reduce angle of attack. Once angle of attack is in the blue range and airspeed around VREF, begin to add power slowly and recover. During this stall, altitude loss was 320 feet, maximum pitch attitude 12 degrees. Note that power was not added until the airplane was flying again. And now let's look at accelerated stall. Again, this shows that the angle of attack indications are relative to the airspeed as well as the attitude and demonstrates the early too slow and thus early stall warning provided by the angle of attack system. Again, pay attention to the angle of attack indicator and the airspeed. Here, VREF is 106. At 30 degrees bank, we are just beginning to add Gs. The airspeed is 108 knots. At 45 degrees bank and 1.4 Gs, airspeed is still 108, but note the angle of attack is higher due to the G loading. At 59 degrees, now at 2 Gs, airspeed is still 108, but at a still higher angle of attack, we get the too slow voice alert. Now we are close to shaker. Next, the shaker activates. And if you have the voice alert, the stall in your headset. Now, airspeed is still 106, but the bank angle is 65 degrees. We are now just prior to aerodynamic stall. Watch what happens at the recovery just after shaker and stall. The recovery is lower the nose to reduce angle of attack, reduce the bank angle, then once angle of attack is in the blue range and airspeed around VREF, begin to add power and recover. During this stall, altitude loss was 320 feet, maximum pitch attitude 7 degrees, maximum bank angle 65 degrees. Stall airspeed about 105. Note that power was not added until the airplane was level and flying again. So the important point here, as your angle of attack increases, your margin prior to stall decreases. Again, remember, angle of attack is the critical parameter here. So why angle of attack over airspeed? Angle of attack provides a direct measure of margin prior to stall. Airspeed needs to be adjusted for weight, load factor, bank angle, and others, but these are the big ones. The airplane will always stall at the same angle of attack, but not at the same airspeed, as demonstrated in the accelerated stall video. If you recall, at the higher load factor, the stall speed of the airplane was about 105 knots, well above the wing's level stall. Thus, with a direct measurement of angle of attack, as provided by the Alpha Systems angle of attack as installed in the MU-2, the pilot has a direct measurement of margin prior to stall. The military reduced fatalities significantly using angle of attack systems. Navy carrier flight operations rely exclusively on angle of attack during approach to landing. The NTSB and the FAA determined that a large portion of fatalities in general aviation airplanes occur on the base to final turn, in slow flight, and accelerated stalls. Angle of attack systems can help prevent this accident scenario. Because of these statistics, the FAA developed an initiative to get angle of attack systems installed with a reduced certification barrier that lowers system costs and thus increases adoption rates. So now let's talk about how to use angle of attack. First, use angle of attack as a cross-check of VREF. The angle of attack indexer matches the MU-2 VREF at all flap settings, 0, 5, 20, and 40. This provides weight-adjusted approach speeds per the airplane flight manual and checklist. thus a proper safety margin above stall. Use the angle of attack indicator's blue donut to verify VREF. If a large difference exists between angle of attack indication and checklist VREF, something's awry. Verify the gross weight or disregard the angle of attack indicator and have it checked. The indicator on the lower right shows the indication to be expected at VREF for a normal approach. Remember that the angle of attack is secondary and the checklist and airspeed are still primary references. Use the angle of attack to help with normal airplane flight manual required adjustments for crosswinds, gusty winds, and icing. All of these still apply and need to be used. For gusty crosswinds, as always, add half the steady state wind plus all the gust. Remember not to exceed 10 knots. The indicators show indications to be expected for VREF corrections of VREF plus 9 and VREF plus 12. For icing will change the lift coefficient to angle of attack characteristics. A wing covered with ice requires a higher angle of attack to provide the same lift. On the other hand, stall angle of attack will be reduced compared to a clean wing. Remember, the MU-2 checklist says, when landing with any ice accumulation on the wing, increase the computed VREF by 15 knots. This quantifies what happens to the wing lift characteristics for the MU-2, and this has been validated by flight test. Use the angle of attack segment shown here, VREF plus 15, for icing when we're determining the proper speed to use for the approach. Angle of attack probe heat is provided whenever the right-hand pitot heat is turned on. Like all airplane systems, this needs to be verified functional prior to relying on it in icing conditions. Remember that any airplane flight manual or checklist adjustments to VREF still apply and need to be used. Now fly the airspeed as just verified with the angle of attack indicator. Remember, the airspeed indicator is still the primary reference, especially during IFR approaches, since the glide slope and localizer indications are on the instrument panel near the airspeed indicator. The big benefit here, you know the margin from stall. It is not an arbitrary 5 knots for the wife, 5 knots for the kids, and 5 knots just for good measure. The graphic shows where on the lift curve slope each angle of attack indication falls. The real benefit? Knowledge, not arbitrary adjustments. At minimums, begin the transition to outside. Keep the angle of attack in your peripheral vision. The goal, by 50 feet, at target airspeed, at target angle of attack, and then at 50 feet start a normal deceleration. Be aware that at touchdown, or just before touchdown, you may hear the too slow message. Angle of attack is in the peripheral vision, even when focusing outside during the final landing flare and touchdown. There are significant benefits to using angle of attack. Fly this way, you will fly stabilized, consistent approaches. You will learn to fly by the numbers. You will achieve consistent touchdown, landing, and runway distances. Typically, less tire and brake wear will result, as landings will tend to be at the proper speeds. You will become a more precise and confident pilot. In the pattern, keep the angle of attack indicator in your scan. Monitoring angle of attack will help you maintain proper stall margin, especially when turning. In a turn, the load the wing must carry increases. In order to maintain altitude, angle of attack must also increase. If proper profile speeds are maintained, stall margins will be well above the blue donut. Anticipate adding power to maintain airspeed and angle of attack. Use the angle of attack indicator to help with that. Even while scanning for traffic in the pattern, angle of attack will be in your peripheral vision. This will help maintain proper stall margins, especially when your head is out of the cockpit. On descent to landing, angle of attack can help you fly a precise glide path. Use angle of attack to help control the pitch angle and airspeed. Use power to control descent rate. Remember during your IFR training the mnemonic that your instructor used? Pitch controls airspeed, power controls rate of descent. This really means pitch controls angle of attack. And now you know why this is important. As you learn to use angle of attack, remember to point the nose in the direction the angle of attack arrow indicates. When slow, the angle of attack arrows point down. Push the nose down. When fast, the angle of attack arrows point up. Raise the nose. The angle of attack indexer is an intuitive indicator. On takeoff, the indicator becomes alive after liftoff. As the airplane accelerates, keep the angle of attack indicator in your peripheral vision. Plan to accelerate past the blue donut into the yellow and then green range as the airplane climbs away from the runway. You will achieve your expected normal acceleration profile. So now let's talk about the real safety benefit of the angle of attack system. It's the non-normal scenarios. And let's talk specifically about 3 of them. We're going to talk about circling approaches, we're going to talk about engine failures on takeoff, and we're going to talk about missed approach. So imagine, you've just shot a great minimums approach. Now you need to circle. Where is your attention focused? Often outside the cockpit, looking for the runway. Out of the corner of your eye, the angle of attack display shows red chevrons. Brings your attention back into the cockpit, paying attention to airspeed, altitude, and bank angle. When you're looking out of the cockpit, if you're circling to the right, you're looking right through the angle of attack indicator, you'll see it directly. If you're circling to the left, it'll be in your peripheral vision. You notice that. Red chevrons bring you back into the cockpit instrument panel. This alerts you to the threat of low airspeed, high bank angle, high Gs, possibly low altitude, providing time for you to correct the situation while there is still plenty of margin from stall. If you react appropriately, lower the nose, add some power, angle of attack turns to the blue donut, all is good. But suppose you do not notice the red chevrons. You will next hear the too slow message in your headset.
Too slow.
Immediate action is required. It is time to react now. Lower the nose, reduce bank angle, and reduce drag prior to potential loss of control. Abandoning the landing and executing a missed approach may be the safest action to take. Tests conducted on the MU-2 show that there is ample margin at the voice alert to correct the situation if prompt action is taken. Now let's talk about an engine failure shortly after liftoff. In this first scenario, let's assume there is sufficient runway remaining to land and stop, just like the MU-2 training scenario we are taught. Keep the angle of attack indicator in your scan. You can focus outside and execute an emergency landing. Keeping the angle of attack indication in your peripheral vision, you will be able to keep the airplane flying with adequate stall margin during this critical maneuver. Now let's consider the case where there's not enough runway remaining. If you have proper acceleration, you are in good shape. If acceleration deteriorates, angle of attack is another tool to help alert you to a potential critical situation as you transition to single engine climb. The angle of attack indicator can help in several ways. If the airspeed or angle of attack deteriorates away from breath climb towards stall, red chevrons will be the first indication, alerting you to take action. Lowering the nose to increase airspeed is the appropriate response. Using the indicator, always with angle of attack, red chevrons mean lower the nose to keep flying. But let's continue and say you do not notice the red chevrons. Too slow, voice alert in your headset will be the next indication. It is now a critical problem, and the time for action is now.
Too slow.
At a voice alert of too slow, the airplane is at or near the single engine minimum control airspeed, well below single engine rate of climb speed. Immediate action is required. Lower the nose, reduce drag prior to potential loss of control. Feather the failed engine when time permits. Check gear position and landing lights to reduce drag. Leave flaps in their takeoff position until clear of obstacles, at which point accelerate and retract flaps on schedule. Once rectified, the climb can continue. Keep the angle of attack indicator in your scan. Let's change the scenario to a missed approach, either multi-engine or single engine. A potential loss of control is lurking nearby. As remember, we rarely must go missed on approaches. This is a non-normal situation. Angle of attack can help alert you if loss of control is imminent. The scenario is virtually identical to the engine failure on takeoff that we just discussed, except if flaps are 40 for landing, immediately select flaps 20. Establish a climb attitude. Keep the angle of attack indicator in your scan. We've just presented 3 potential scenarios. With angle of attack, information is available to alert you of a potential loss of control. It is a visual indication in your view. It provides a voice alert of too slow in your headset. The response is always the same and should be automatic. Focus back to the cockpit instruments. Lower the nose and reduce bank angle. Reduce drag, add power as appropriate, maintain control of the airplane. The key takeaways from this: if yellow chevrons point up, all is well with respect to stall margin. If red chevrons point down, it is time to do something. Lower the nose and/or decrease bank, increase airspeed, Increase power as required in a slow and coordinated manner. I'm going to repeat that. The response is always the same. Lower the nose and/or decrease bank. Increase airspeed. Increase power as required in a slow and coordinated manner. Be aware that if the airplane is turning, all these actions will result in the turn radius increasing. If you are in the landing pattern, is the airplane too close to the runway? If on approach to a runway, you may need to consider a go-around. Execute a go-around if a stable, adequate airspeed or reasonable bank angle cannot be maintained. If the too slow voice alert is heard,
Too slow.
immediate action is required. Lower the nose and/or reduce bank angle, and after the airplane is flying again, as indicated by the blue donut, add power, but slowly as required. If on approach, possibly go around. The too slow voice alert will typically sound prior to the shaker. Earlier warning of impending stall is provided. If you hear too slow, there is very little margin from stall. It is time to take action now. So let's look at a normal flap 20 landing. Here we're starting with the ref speed of 106 knots. This is a flap 20 landing. Note as the airspeed wanders, the angle of attack display matches as we get a bit slower and a bit faster due to slight turbulence during the approach. At about 50 feet, start a slow deceleration and bring the nose up slightly, readying the airplane for touchdown. So, key topics to remember from this video. Stall is about angle of attack, not airspeed. The airplane will always stall at the same angle of attack. Lower the nose to reduce angle of attack to prevent stalls. Thank you for listening. Fly safe.